In this video, we're going to look at things like the limit as x approaches infinity of one polynomial p of x over another polynomial q of x. And the first thing we need to learn about to do these problems is what the degree of a polynomial is. The degree of a polynomial. So what is the degree of a polynomial? It's the largest exponent in the polynomial. The largest exponent in the polynomial. So what do I mean by that? So let's look at an example. So let's say we have the polynomial x to the 9th plus x squared plus 1. What's the degree of this polynomial? Well, we look at each term. So this is x to the 9th, x squared, and then 1 is really multiplied by x to the 0. And so we're looking for the largest exponent in the polynomial. The largest exponent in this polynomial is 9. So the degree of this polynomial is 9. What about another example? What if we had x squared plus x cubed plus x? What about the degree of this polynomial? So this is really x to the 1. So we have to look at the largest exponents in the polynomial, find the largest one. We have 1, 2, and 3. The largest exponent in this polynomial is 3. So the degree of this polynomial is 3. So the degree isn't too tricky to find. That's good for this type of limit. This limit shouldn't be too tricky to find. There's 3 cases. Let's look at the 3 cases. There's 3 different ways this can go. Okay, so case number 1. Say we have something like this. We have the limit as x approaches infinity of x cubed plus x plus 1 divided by x squared plus 2. So in this example, you could think of this as p of x, the polynomial on top, and this on the bottom would be q of x. So what can we notice about p of x and q of x? What about their degrees? What's the degree of p of x? We look for the largest exponent in the polynomial. That's 3. What's the degree of q of x? We look at the largest exponent q of x. Since this is 2 times x to the 0, it's between 0 and 2. 2 is obviously bigger. So the degree of q of x is 2. So what we're really looking at is that the degree of p of x, we can write that like this. The degree of p of x is 3, and that's larger than 2, which is the degree of q of x. Now what happens when the degree of the numerator is larger than the degree of the denominator? That means that as we let x get larger and larger, the numerator is going to grow larger and larger because we're going to be cubing one of the numbers on top. So say we had, x goes from 10 to 100 to 1,000. We'd have something like 10 cubed over 10 squared, and then we'd have 1,000 cubed over 1,000 squared. All right, so the top is growing a lot faster than the bottom. What does that tell us if the top grows a lot faster than the bottom? That tells us that this limit is going to end up going to infinity. So the limit as x approaches infinity, x cubed plus x plus 1 over x squared plus 2 is going to equal infinity. And this happened because the degree of the numerator was greater than the degree of the denominator. And that's going to be case number 1. Case number 2, let's look at this problem. We have the limit as x approaches infinity of x to the 7th plus x squared plus 5 divided by x to the 11th plus 2. So in this first example, I'm just going to separate these cases with a red line. In this first example, the degree of the numerator, the top, was greater than the degree of the denominator. How about in this case? What's the degree of the denominator? It's 11. And the degree of the numerator is 7. So in this one, the degree of the denominator is larger. So what's going to happen there? As x gets larger and larger, and we plug in bigger and bigger numbers, the denominator is growing much faster than the numerator. So that means we're going to get terms like 1 over 10, maybe 5 over 1,000. I'm just making these up, but I'm trying to show what something would look like if the numerator was growing slower than the denominator. Maybe 10 over 10,000. This kind of sequence, the numbers are getting closer and closer to 0. So in this limit, the numbers are getting closer and closer to 0. The limit's equal to 0. And that's because the degree of the denominator is larger than that of the numerator. 11 is bigger than 7. Okay? And then for case number 3, we've done one where the top was bigger than the bottom is bigger than the top. What about if they're equal? What if we have something like this? We have the limit as x goes to infinity, 5x squared plus 3 divided by 6x squared plus 100. What's the degree of the top? It's 2. What's the degree of the bottom? It's also 2. So how are these growing differently? They're really not. Now, if we plug in 10, 100, 1,000, neither one is growing faster than the other. Both numbers are being squared, so they're essentially growing at the same speed. So what we can think about, 3 and 100, these don't really matter. They might matter if you just plugged in x equals 5 or x equals 10, but as you get closer to infinity, these small constants don't really do much. You can just imagine that you could cross them out. if we cross them out, then we're left with the limit as x approaches infinity, 5x squared over 6x squared. And now we can just cross out these x squared terms, and we're left with 5 over 6. Okay? So because the degree of the top and the bottom were the same, the answer, all we have to do really is look at the numbers that are in front of the terms with the highest degree. Those numbers are 5 on the top and 6 on the bottom. That's what the answer ends up being.